Okay, so I guess start. Today we have our own Minjae who agreed to give this talk just a couple of days ago. And
Literally a couple of days ago.
Yeah. And he will talk about bootstrapping, equilibrium, and non-equilibrium quantum systems.
Thank you. First of all, I have to make it clear that I'm not Ryan Thorngren. Unfortunately, he couldn't make it today. So I'm the emergency substitute speaker, but hopefully I can still entertain you. So I'm going to tell you about bootstrapping, equilibrium, and non-equilibrium quantum systems. This is based on a series of works that I have been involved in recent years, together with these wonderful collaborators. And this is my first slide. Looks familiar. When we talk about equilibrium, what we mean is thermal equilibrium, and we care about this number called temperature. It's because everything depends on it.
It's in the wrong unit.
No, yeah, maybe yeah, my apologies.
No option can be.
Yeah, you can't put my bad. Yeah, there should be some extra stuff here. Yeah, my bad. Yeah, so say you have your favorite quantum system, you can subject it to a Q-sheet bed at constant temperature T, and then you can ask what are the properties, and especially how do they depend on the temperature. After a while, the system is going to equilibrate, and you are going to describe your system in terms of this so-called Gibbs state or thermal equilibrium state. Of course, once you tell your experimental friends about this type of setup, they will tell you that, well, in real world, that's too idealized, and there are also always going to be some type of quantum dissipation. So later we are going to study one specific form of such dissipation. So this is the usual Hamiltonian time evolution, but there are going to be extra terms which are responsible for such dissipation. And now generically, the dynamics is coming from some non-equilibrium dynamics. Okay? So even though this is a headache for our experimentalist friends, for theorists like us, it's an exciting playground. We can ask, for example, are there steady state which stay invariant under the time evolution? Because those are the ones which dictate the late time behavior of the system. And if there are they unique? And also, if they are not unique, there are multiple, there can be phase transition between unique to multiple, and that gives some notion of non-equilibrium phase transition. And in fact, in recent years, there have been a lot of intriguing developments in condensed matter, quantum info, quantum optics, and so on about such non-equilibrium phase transitions. In both cases, we actually run into issue of something called ensembles. Okay? So consider thermal equilibrium. It's a highly mixed state. So naively, it seems like every state in some basis contributes to this quantity. So it seems to suggest that we have to enumerate contribution coming from all states. But for quantum systems with large number of degrees of freedom, this sounds like a hopeless task. So we naturally get to ask about some alternative approach. And today I'm going to tell you about bootstrap approach to this thing.
So when you say that, you mean that in the bootstrap, you'll directly compute some observables, not rho itself?
That's right. Yeah, I'm going to, in particular, compute the expectation values evaluated in those density matrices. Yeah, and yeah, story is not much different from non-equilibrium. Generically, states of interest are highly mixed states. So what is bootstrap? It's a kind of a framework or approach. Say, we are theorists. We write down a theory, hoping that it's consistent. Then you might think about a situation where just these axiomatic consistency conditions may actually buy you something non-trivial. So in Bootstrap, we impose only one must be true. And in practice, for today, we are going to impose a finite subset of defining properties of the density matrix rho, which we are going to study, such as thermal equilibrium. And the end result will be that we are going to obtain rigorous bounds on the expectation values evaluated in such density matrix. Okay, sounds like a nice plan, but you might ask, why do we care about such an approach? First, a bit formal answer is that you keep the rigor. Okay. And this rigor even applies to cases where you have infinitely many degrees of freedom. So you have infinitely many degrees of freedom in your quantum system, but there are still, some defining properties which you can explicitly enumerate. And if you impose finite subset of them, they still are something that must be true for your system, and therefore you preserve the rigor. But more importantly, it turns out that sometimes it is the only way. Okay, there are going to be interesting physical examples that I'm going to tell you later. Where I currently do not know of alternative approach.
Even numerics?
Even numerics. Yeah, so I'm going to tell you. So I told you about, I told you that Bootstrap is about defining properties. So we have two players today, equilibrium and non-equilibrium. So let's start with equilibrium. We fix the temperature T, and this is what we are after. This beta is inverse temperature. And for infinite system, this type of expression is hard to make sense of. But that's the reason why people actually came up with defining properties, which is written just purely in terms of expectation values. And this is a celebrated KMS condition, which is basically the definition of the thermal equilibrium. It says, for any operator O1 and O2, you consider this thing, and they should equal. So what is this? This left-hand side is Euclidean two-point function. So this O1 is located at Euclidean time beta, which agrees with the inverse temperature of your thermal equilibrium. And O2 is located at 0. And they should equal O2 times O1. See, these two things are now switched. But then they are located at the same point on the Euclidean time. Okay. It's easy to derive this from this expression when this makes sense. And as you can see here, this is kind of a constraint on the Euclidean two-point function. There's equivalent but less well-known constraint called energy-entropy balance inequality. I'm going to call it EEB inequality. And what's nice about this is that it's purely about one-point functions. Okay? And let's start with the zero temperature. So in zero temperature, thermal equilibrium means ground state. And what's the definition of ground state? It's the minimizer of the energy. Okay? So say you already start with the ground state, but apply any deformation by this operator O, energy must increase. The change in the energy can be explicitly written in this form, which nicely combines into this O-dagger Hamiltonian commutator with O. And this being positive is called ground state positivity, and is one of the defining properties for the ground state. Now, what if you have non-zero temperature? You repeat the exercise from statement that you learned in STEMMAT, which is that thermal equilibrium is minimizer of the free energy. So you repeat the exercise saying that, if I am already at thermal equilibrium and apply any deformation, it must increase free energy. This is easy to say, a bit complicated to carry out, but fortunately for us, Arc and Cell all the way back in the 70s carried this computation out. This is the result, okay? So this left-hand side, you recognize that is what we already have seen here. So it's changing the energy. Right-hand side is roughly speaking, changing the entropy, as you can recognize from this log appearing here, okay? Any question on this?
You said something that it was equivalent?
Yeah, these are equivalent.
The two conditions are equivalent.
Under extra assumptions like stationarity and so on, I'm going to soon give you a full set of defining properties. Yeah.
What does it mean, defining?
Sorry?
Why these properties are called defining?
Because, you can, okay, another way to say this is that you can take this as a definition of thermal equilibrium. That's what I meant, yeah. So if you have set of expectation values that satisfy all of these things for all your local operators, then that's the definition of thermal equilibrium.
There's no other density matrix that satisfies these, I guess.
There may be multiple, yeah.
Multiple.
For example, in the symmetry broken phase for the Ising model, that's the Ising spin chain, we know that there are actually multiple density matrices in zero temperature, let's say. Yeah.
I don't get it. Isn't that rho e to the minus beta h, isn't that a unique expression?
Good. That's the reason why I was referring to systems with infinitely many degrees of freedom. So when you're in the case where you have only finitely many degrees of freedom, then yes, this is unique state. And all of these things, you basically have some unique answer.
Mm-hmm.
But for systems with infinitely many degrees of freedom, where you may have phase transition, for example, Ising model, you know that in the low temperature phase, you actually allow for infinitely many density matrices. And for those cases, you can actually find infinitely many set of expectation values that satisfy this defining property. Good. Okay, let's move on to non-equilibrium. There are lots of non-equilibrium dynamics that you can think of, such as quantum circuit, for example. For today, I'm going to focus on something called Lindblad dynamics, but the idea is straightforwardly applicable to other types of non-equilibrium dynamics. This is a definition of Lindblad dynamics. Okay. So this is the ordinary Hamiltonian time evolution, but you have extra jumps. This gamma is some real number. This LK is something called jump operator. It's a linear operator acting on your Hilbert space. And it's roughly speaking modeling some type of dissipation of your subsystem degrees of freedom to the environment. It's the most general time evolution you can write down under some technical assumptions, such as completely positive, trace preserving, Markovian, blah, blah, blah. Physics-wise, this is a good description when you have a large environment, which is weakly interacting with your subsystem. And your environment quickly forgets about the feedback coming from the subsystem.
What is the sum over there?
This is some index set that's up to you. Yeah, you basically, this is kind of phenomenological model. I'm going to soon tell you one specific example. Indeed, let me just tell you how it looks like. Okay,
There's
maybe
a notion of complete set of Lindblad. Right? There's a notion that you can write the most general set of it.
Lindblad.
Oh, sorry, can you repeat?
I think there's some notion of that you can write some the complete set of Lindblad operator.
Complete set of
All possible Lindblad
Yeah, yeah,
operators.
yeah.
So I think that the sum usually goes over the whole set.
Oh, that's right. Yeah.
Yeah.
Okay. One of the things that we are going to be interested in is the steady state, because these are the ones which stay invariant under this time evolution, and they are going to therefore be responsible for the late time behavior of your system. So it's one of the first things that you want to study. And in order to phrase everything, all this unambiguously for even systems with infinitely many degrees of freedom, we turn this into time evolution of operator expectation value, which is easy to do from that. And then when that equals 0 for all operators, you can take that as the defining property of this steady state.
So you're always going to assume it's Markovian. Is that?
Oh yeah, that's right. I'm always assuming it. Yeah. I mean, of course, this is a strong assumption for many situations.
Right.
Yeah. Yeah, indeed. Yeah.
Otherwise, you write some other master equation.
That's right. Yeah, you have different types of master equation.
Yeah.
This philosophy goes through. Yeah.
So
Yeah.
one of the two signs is wrong.
Sorry.
Forget. There is a sign mistake.
Sign mistake.
He's just kidding. No.
Okay.
No, I'm not kidding. It's a fact, but it's not important.
Sorry. Here's a sign mistake somewhere.
Yeah, in the first term, so minus I,
I think this is right,
and then
because you want to come from here and then take the trace of row of O, and I think it correctly translates to plus sign.
yeah, that's true.
Okay. So if this were your first to say Lindblad dynamics, let me give one example. Say your quantum mechanical system has annihilation and creation operator. Okay, and take this jump operator to be annihilation operator. What this is doing is that it's kind of spontaneously trying to emit your quanta to the environment. That can be seen by considering time evolution of number operator, and contribution coming from this jump operator is minus gamma times number operator expectation value itself. So you can literally see that it's the dissipation effect of your quanta. Good. This is one slide summary of today's talk. Okay, so I told you about some defining properties. This is complete list. Okay, we have 3 columns. One is, so first row is the objectives in each case. First is equilibrium 1 point. We are at thermal equilibrium. We want to compute some operator expectation value there. Second is Euclidean 2 point. We have O1 tau evaluated U, some specific Euclidean time U, and O2 at 0. Okay. And finally, for the Lindblad case, we are going to be interested in steady state 1 point function. Okay. This is what we want to compute. Okay. And now let me give you the defining properties. In all of these cases, very important defining property is positivity. We know that density matrix must be positive. It's coming from the fact that probability is positive. In terms of expectation values, it translates into positivity of this matrix M, whose ijth elements looks like this, where all i's are spanning the operator basis. For the Euclidean 2 point function case, you can promote this to depend on the Euclidean time, and you get some analogous positivity matrix, which is function of tau. Okay. And finally, for the Lindblad case, we have the same thing as before. And now let's discuss time evolution. For the equilibrium 1 point, it's a stationary state, so it does not time evolve. So therefore, Hamiltonian commutator should give you 0 for any operator O. For the 2 point case, we have explicit tau dependence. Therefore, if we hit by derivative in tau, we get this Hamiltonian commutator. Okay? For the Lindblad case, steady state equation is what I already described in the previous slide. And this completes the 3rd column. Okay? For the first 2 columns, we have temperature-specific constraints. For the first one is the energy-entropy balance inequality that I described before, which is basically saying the free energy must increase. For the second one is the KMS condition, which is kind of a boundary condition for on the space of your 2 point functions. Particular cases where you take the temperature to be 0, in that case, you replace this by ground state positivity, where you basically take this to be positive and have Euclidean time dependence for your operator O. Then you get this positivity. Okay. So what I'm showing you here is basically the definition. Okay? You can literally take this as a definition of equilibrium and non-equilibrium steady state. And what Bootstrap is going to do is the following. So these are what we want to compute for some specific operators or tildes. Okay, we are going to say we are going to plug these things into the computer. Okay, computer is gonna perceive these expectation values as variables. So now we are looking at the space of expectation values. And then we ask the computer, given all these constraints, do your best to find the minimum and maximum of this guy. Okay. Given all these defining properties, find the minimum and maximum of this guy. Sounds like a nice plan, but you may ask, is it feasible in practice? Turns out that it is very feasible.
Sorry, minimum or maximum of what?
Specific expectation values of your interest. Yeah, it's up to you. It's your choice. In each of these cases, this equilibrium 1 point, Euclidean 2 point, steady state 1 point. So you can compute internal energy, let's say, as function of temperature.
So, so the last line, you have this provide constraints to include in the bootstrap equations, right?
Oh, sorry, can you repeat that?
In your last line there, all of those inequalities, you provide constraints to put in your bootstrap equation.
That's right. That's right.
Okay, so the first bracket there, this log of O dagger O divided by O dagger, this reminds me a lot of the Crookes relations, where you have like work in one direction, work in the other. You have like work in the direct version in the reverse. It must be larger than 0. But I think there are constraints in non-equilibrium as well, right? Like Crookes, non-equilibrium Crookes equations that you might be able to include there.
That may be true. I haven't thought about that. But at least for today, this is all that you need. So let me tell you one thing. There always are extra constraints that you may want to impose on top of this. Okay, there may well be, and they may actually help you get better bounds, let's say, and that often happens. Yeah, but yeah, here I'm just literally showing you only the minimal defining properties. Yeah, so it's your choice to include more if you want. Yeah. So one very nice thing is that all these defining properties turn out to be convex constraints on the space of expectation values. Okay. And some of this convexity is hardly emphasized in ordinary quantum mechanics courses, but I think it's important to emphasize that. So what is convexity? This is one example of convex region. You pick 2 points in it, draw a line, the entire line is contained. What it implies is that if you find the local minima, say for this y-axis, that automatically gives you global minima. Okay? Therefore, if you just do any gradient descent type method, you are going to get global extrema. And this is the reason why bootstrap is very natural. Some of this convexity is just built in the definition of equilibrium and non-equilibrium. And bootstrap is an approach to maximally make use of that. Is this clear?
So can you say which property of the equations you have? So to see convexity in what you had?
Yeah, so.
Is convexity of log or what is
Yeah, so yeah, let me tell you. Yeah, so first of all, this type of matrix positivity, these matrix elements are linear in the expectation values. And this constraint is actually convex constraints on the space of expectation values. Meaning that if you find 2 points which satisfy this positivity to set up expectation values, take any weighted average that again satisfies this positivity. Likewise, for all these linear equations, because they are linear, this one is the most tricky thing. Okay, turns out that this is also convex constraint. Yeah, and it's kind of similar idea as many of the entropy inequalities that you run into in quantum info. Yeah, they have some built-in convexity. This is one of those. So we can obtain this global min and max. What do they mean? So we want to minimize or maximize objective expectation values subject to all these constraints. And the end result is that we are going to get rigorous lower and upper bounds on the actual physical answer. Okay, this is because we are imposing only one must be true. And this job of finding min and max can be efficiently done using convex optimization solvers, which are available in various forms. One is SPP, semi-definite programming dealing with matrix positivity. This is more recent one called quantum information conic solver. This is developed to inherently deal with logarithmic inequalities that you face in quantum information theory. In particular, energy-entropy balance. So
is there something that a priori guarantees that there would be finite min and max? The space of expectation values might go off to infinity, right? So that doesn't necessarily have to be a bounded region.
Right. So very good point. So indeed, even more, what you can ask is like, if this is guaranteed to say, give you like, even if you get finite things, is there a guarantee that you are going to have some convergent result? Yeah. Yeah, if you include more and more bootstrap constraints. The answer is that typically there is no general proof that you can actually get a good result, roughly speaking. But at least for good enough quantum systems where your Hamiltonian has some notion of, say, locality, then it is expected that by including this type of constraints in some local operator basis, you are able to actually approach to the physical answer that you expect. This convergence proof is not yet proven for many of the quantum cases, but in the classical stem cases, if you repeat similar argument, indeed I proved the convergence with mathematician Shin-sun several years ago, and very recently there was a paper by optimization group showing that convergence in the high temperature regime is exponentially fast. Yeah. So yeah, for the quantum case, the proofs are not there. So mathematically, I cannot give you any answer, but physically, if you have locality notion, then I can tell you that you always get something nice.
Could you give me some intuition about that?
Yeah, so say you have quantum spin chain, okay? Then basically this H has some nearest neighbor term. So if you have, say, n side operator here, you're generically gonna get some n plus 1 side operator. And basically in Bootstrap, you cannot impose all these infinitely many constraints. So you are going to truncate on this, say, side length for your operator. And when that reaches some point which is beyond the correlation length of your system, then you expect that your Bootstrap constraints are actually going to be strong enough. Yeah, basically there's some physics intuition, which is that you want to consider, say, correlation length versus the length of the operators that you are considering.
And if it's critical, then
yeah, criticality is typically the most difficult region for Bootstrap. Yeah. Okay, so simple example. Take the equilibrium 1-point Bootstrap that I told you just now. Single particle quantum mechanics. The way we teach our computer that we are dealing with quantum mechanics is by imposing the operator relations, such as canonical commutation relation. So you are going to provide this type of information to your computer. One example of this equation is this one. So you set this to be 0. And as I already mentioned, you need some type of cutoff in the Bootstrap constraint. So here, say we consider operator expectation values, where operator consists of words of x and p up to some length 10, let's say. Okay. You run all this machinery, and this is a result of energy as function of temperature. And this black region is the tightest Bootstrap allowed region in this plot. It's pretty tight, and this red line is the result of enumerating the first like 20 or 30 energy eigenstates explicitly, and they are very nicely consistent with each other. So you can see that in this toy example, it works really well. So let's go to a non-trivial example. This is our first example of matrix quantum mechanics. So a bit of physics. This is a matrix version of the single particle quantum mechanics that I just described. Instead of x and p, you promote them to Hermitian n by n matrices. Okay, so that's what these ABCD labels are about. They range from 1 to the n. And you can have multiple number of them, okay? And they obey canonical commutation relation. It's a very straightforward extension of single particle quantum mechanics. Hamiltonians typically look like this. It's trace of something, kinetic term, mass term, and there are commutator square type interaction term. And this is familiar from gauge theory. And in fact, you can obtain these type of theories by dimensionally reducing higher dimensional gauge theories. And notice in particular that here I'm explicitly including 1/n factor here, where n is coming from n by n matrix. Later, we are going to be interested in large n limit of these theories. And when you have this 1/n, this limit is Hooft limit. Okay. The reason why we care about this type of system is because general expectation is that these are due to quantum gravity and string theories, and there are explicitly known examples. In particular, you may want to ask, some black hole thermodynamics and quantum gravity and so on. They basically translate to the study of thermal equilibrium in this system. This is easy to understand. I mean, any undergraduate who just took quantum mechanics would understand what this system is about. Okay? So you might say, no.
This teacher. It's real well data.
N square number of particles.
So this commutator in xi and xj, is that commutator with respect to the indices?
Right. It's commutator for the matrices, not for the operators.
Not
Yeah.
for the operators.
That's right. Yeah, as an operator, they commute. Yeah. Thanks. Yeah.
Is there, and you said there's an explicit assumption of working in the Hooft limit?
I didn't make that assumption yet. Soon I'm going to take n to both finite and infinite. So it's just quantum mechanics that's going to study. It turns out that it's not that easy. So let me give you one specific example. It's called BFSS matrix quantum mechanics or derive matrix quantum mechanics. I didn't give you Hamiltonian here, but it's basically one of those maximally supersymmetric ones. So there are bosonic fermionic matrices with some SUSY. So this one, when you take large and hoofed limit and do the small temperature expansion, turns out that the dual supergravity description is valid. For example, if you look at energy as function of temperature, so the first line is the leading term in large and second is subleading, and for each of them, you do small t expansion. This first term has explicit expectation coming from supergravity, okay? So this number is not coming from the quantum mechanics side. This is coming from the supergravity side. And this is a very precise prediction of holography. So you might say, oh, let's go and compute this from matrix quantum mechanics. It's like one of the simplest, thing that's just like seems obvious there. It's not easy because low temperature is strongly coupled regime because hoofed coupling has positive mass dimension. Okay. That's the reason why people had to rely on, say, lattice Monte Carlo. This is the, as far as I'm aware, this is the most up-to-date result. So here, this black line is the result from supergravity, and these red dots are the Monte Carlo results. Okay. You don't need to worry about disagreement here because it's only the leading order temperature behavior. But as you can see, the low temperature region where we are most interested in, you kind of get huge error bars, and there's a good reason for that. So there are a lot of subtleties. First is that Monte Carlo can deal only with finite n, but it turns out that finite n, there is thermal equilibrium is actually unstable. So you actually need to take large n limit. Furthermore, you have fermion matrices, so there's a typical sign problem. And low temperature is the most expensive regime because you need large Euclidean thermal circle. But all of these subtleties are absent in the bootstrap formulation that I described to you. Okay? And in fact, ground state bootstrap for this problem dates all the way back to Polchinski in '99. Okay, so let me go into a bit more detail. This is the Hamiltonian. As you can see, there's a UN global symmetry under which X and P's are adjoint. Okay? And there are typically two versions of this theory. One is called gauged model, where you restrict to the singlets. There's also something called ungauged model where you do not make such a restriction. Today, I'm going to focus on ungauged case. For the gauged case, if you have, say, one matrix, then you can literally study the dynamics of the eigenvalues. And in that case, it's analytically solvable. But even for one matrix case, ungauged model is unsolvable. So it's kind of a nice test ground. Another physical reason is that this low temperature expansion that I showed to you, they actually apply both to the gauged and ungauged version. So let's start with bootstrap variables that we are gonna run into. First, you might say, okay, if we have this single adjoint, OAB expectation value, naively it seems like there are n square number of expectation values that we need to worry about. But we know that as long as we are in the state which respects UN, we can use symmetry, okay? And we just have single expectation value called trace code. Similarly, bi-adjoint can be decomposed into these invariant tensors. And in the end, you just have trace of operator expectation values. And what this is telling you is the number of variables does not scale directly with n. Okay, and this is one of the advantages. If you're on Monte Carlo, your number of degrees of freedom literally scales with n, not for bootstrap. On top of that, you can literally take planar limit. Planar limit means strict n goes to infinity limit. Okay, that's because you have bootstrap constraints, which are some expressions of n. And all you need to do in order to take planar limit is to keep the leading order term at large n limit. Okay? Then you land on the constraints which apply strictly to the planar physics. That's how you can directly bootstrap large n model.
This works both in also for an ungauged case, or so your rotational basis to reduce OAB.
Mm-hmm.
You rotate by some UN, right?
Yeah, for the gauged case, you to begin with start with a trace. Because the linear operators which are well defined on the gauge singlet sectors are the ones, are the singlet operators. Yeah. If you're an expert, you also might be familiar with the large n factorization, which is telling you that a large n limit, this expectation value, multi-trace expectation value factors into this one. And if you want to impose this, you can impose this also as bootstrap constraint. Okay, so let me give you one specific result along this line. Take this one matrix quantum mechanism with Porty coupling G. Okay. This is positive Porty coupling, and you can do the bootstrap at finite n, 2, 4, 6, 8, 10. So those are these allowed region. This is energy as function of temperature. You can also do it strictly at infinite n, which is this bootstrap bound. Okay. And again, this infinite n is not the extrapolation of finite n. This is literally infinite n bootstrap. So now I'm going to just focus on infinite n.
What's the vertical axis?
Sorry, it's the energy. So internal energy as function of temperature, Hamiltonian expectation value.
So here it goes to a constant. Why doesn't it also go to a constant in your other case where you have a mass, or were you going to send the mass to zero? You had this theta funny power at low temperature.
Ah, good. So this is massive case. The BFSS was mass least
Oh,
case.
you want mass?
Yeah. So this is actually in low temperature going to be exponential e to the minus something times t. While in the massless case, you have t to the power. Yeah. So that's qualitative difference between massless case and massive case.
But it's E over n squared?
Yeah, n squared minus 1. Just so that in the Hooft limit, I have order 1 number.
Okay.
Yeah. Yeah,
So
Hamiltonian.
this is not the black hole region.
It is. So it's the black hole region for the Hooft limit. It's not the like M theory limit if you do similar thing for the BFSS. But this is the black hole region. So yeah, as you can see here, this is the black hole expectation. And we have explicit n squared here.
It's the D0 black hole.
Yeah, D0 black hole. That's right. Okay, so these are some plots at different coupling values. Again, energy as function of temperature. The tightest bootstrap bound here is this very shallow black line that you can hardly see. It's not a line, it's bootstrap allowed region. It's just that lower and upper bounds are so close to each other that it looks like a line. And this just tells you that bootstrap literally determines the answer almost exactly.
What is L?
Yeah, L is basically the bootstrap cutoff. We are cutting off the to the operators whose length, where you count the words of consisting of letters X and P, whose length is up to 10. Yeah.
Well, you don't need to know anything about the spectrum. Flat direction is nothing for this.
Right. So for this model, there's no flat direction.
Yeah, here's all lifted.
Yeah, that's right. For BFSS, there are going to be flat direction, and indeed, that's the very reason why you need some approach which can directly tackle large n, because at any finite n, actually thermal equilibrium is unstable because of this flat direction.
Well, you could turn on the BMN definition.
That's another option. But for BMN, you actually have Hagedorn phase transition at low but finite temperature, meaning that the behavior is qualitatively different.
And can you bootstrap the equation of state?
Equation of state, good question. I haven't thought about it.
Sorry, isn't this the equation of state? E of t.
Sorry, I thought that.
Nope. I want the entropy as a function of the energy.
Yeah, but that's some derivative of this.
Sorry, you meant energy as function of entropy. Sorry, maybe I misunderstood you.
It's the derivative of your plot, right?
Yeah.
Or something like that.
Okay. If that's what you meant, you can definitely get it. Yeah. Okay, let's compare against some.
Does it reproduce the Bekenstein-Hawking entropy?
Okay, so we didn't tackle BFSS yet. So these models that I'm currently describing, we do not know the semi-classical gravity dual. So one of the long-term goals is to actually tackle BFSS.
Oh, so it's just one. It's just the bosonic part of BFSS.
Yeah, that's one matrix engaged.
one matrix.
Yeah, one matrix engaged.
Okay.
Yeah, but yeah, indeed one of our long-term goal is to tackle BFSS. So you can compare against some analytic expansions in low temperature. Adjoint gap dominates. High temperature, you can do pipe interval Euclidean thermal circle, and Matsubara frequency most decouple. So this is what you get. So here, this is a very strong coupling G equals to 50, and this black line is the bootstrap result. Okay, you can take this as an exact result. And this orange dotted line and blue dotted lines are basically low and high temperature expansion respectively. And you can see that over a wide range of temperature, it deviates a lot. And this is demonstrating the power of bootstrap. Okay.
Does the high temperature result ever goes to the bootstrap?
Yeah, at very high temperature, it's supposed to go to the bootstrap. Just like at very low temperature expansion goes to the bootstrap. But what I wanted to emphasize is that there's a wide range of temperature where these expansions, neither of the expansions are good. We indeed tried to include sub-leading corrections on top of this. They didn't improve the discrepancy. And another question you can ask is to make this G negative, okay? So naively, it's a negative Cordy coupling, so upside down potential. It's unbounded, everything tunnels through, and system is unstable. But turns out that this tunneling rate is suppressed exponentially at large n, meaning that as long as your G is not too negative and above this critical value, you can find finite energy normalizable ground state at large n. now we can ask further question. When this G is with this range, can a thermal equilibrium at some specific temperature T exist? Our intuition tells us that if you crank up the temperature too high, you're gonna make the system unstable. So there should be some upper bound, critical temperature, TC. And I don't know how to obtain information about this TC using other methods, but Bootstrap knows how to do it. Say, given this negative coupling, if Bootstrap finds constraints to be infeasible at some specific temperature T star, then you know that it provides rigorous upper bound on TC. Okay? What's happening is that you are plugging in constraints into a computer, but computer may complain to you saying that, hey, they contradict each other. But these constraints are coming from defining property of thermal equilibrium. So if they contradict each other, we know that there is no thermal equilibrium.
Sure. How does G enter the bootstrap constraint?
Yeah. It enters via the Hamiltonian constraint. Yeah, so for example, here we have Hamiltonian.
I see. Yeah.
Yeah.
Okay.
So you get inequality, is there a bound on the error? Is it known that if you add more operators, it won't, it's monotonic in some sense, or
It is monotonic because you are always imposing more constraints. Yeah, if you impose more constraints, then you are always gonna guarantee to get better and better and better bounds.
Okay, big, can one estimate then the size of what's missed when you truncate at some number of operators? Is it a good
estimate?
Yeah.
That's exactly the difficult part. So if you want, that's basically related to the convergence rate. And yeah, that convergence rate has been shown only for classical Steinmetz cases so far. Yeah. So if you're a mathematician who cares about this type of convergence, then I think it's a interesting problem. The expectation is that probably convergence in the gapped case is related to the gap itself. That's the natural expectation. But yeah, I don't have any mathematical proof along that line. So here's the result of this negative G near criticality. This is the T star where computer complains to you that it's infeasible. Therefore, this provides upper bound on the temperature, critical temperature. And once you collect that as function of G, you get this very nice plot. So thermal equilibrium is allowed only within this region. Okay, outside there's no thermal equilibrium. And again, let me emphasize, any finite end method can never address this physics because there's tunneling, finite rate of tunneling.
So at small g, do we know the behavior of TC?
Not quite. You mean near GC? Or
small g, negative
near zero?
zero.
Near zero, I don't know. Yeah, at least I don't know. Near GC, there is a old paper by Gross and Klebanov studying this, and they study some universal behavior of this critical temperature. Yeah, so there is some information there. This is preliminary plot for the commutator squared interaction for two matrices. This is only for words up to length 4, and you get still non-trivial bounds. And again, our long-term goal is BFSS. Yes.
You have a sense of what sets the scale, like for this is G strongly interacting, so that it's the bound is not as good, or
Oh yeah, I guess it's basically the mass scale compared to G, roughly speaking. So there are not that many scales here. One is temperature, and the other is basically mass over, say, some power of G. Yeah, so I guess that's what's setting how strong the bounds are.
So the intuition is that for more strong interacting things, you need bootstrap bounds are weaker.
Yeah, so you need more and more bootstrap constraints. But in fact, already for this one, for one matrix quantum mechanics case, strong coupling was not much of an issue. So, yeah. And this one was obtained just by words up to length 4, while the previous one like up to length 10. So I mean, once you increase this, it's pretty probable that this is also going to get very narrow. Yeah.
So in other kind of bootstraps, usually the boundary corresponding to something special.
Right. So for example, if you look at this thing, you can see that boundary is something special. That's exactly the criticality.
Criticality.
Yeah. Okay, let's move on to a 2-point bootstrap. Actually, Henry Lin gave a nice talk last quarter about this, so I'm going to be only brief. So this is a reminder about Euclidean 2-point function bootstrap. We are after Euclidean 2-point function subject to positivity, time evolution, and KMS. Okay? One technical issue is that this 2-point function is function of tau, so it's coming from infinite dimensional space. So it seems impossible to scan over the entirety of them and find min and max. Okay, and there's a trick going to which relies on dual problem. So if you give this to your undergrad who just finished taking calculus, they will say, let's introduce Lagrange multipliers. Okay, so this is your objective which you want to minimize. And you have a whole bunch of Lagrange multipliers. This is one example. This is imposing time evolution equation. And this is basically time evolution equation written in some manner. And you have Lagrange multiplier lambda of tau. And dual problem is obtained by varying with respect to original variable. Okay. In the end, your dual problem is going to look something like this. You want to maximize something subject to convex constraints on the Lagrange multipliers, which are functions of tau. This is still infinite dimensional, but things are nice now. So with duality theorem tells you that this max of the dual always lower bounds mean of the primal original problem. Okay. And what this is telling you is that, okay, this mean is what gives rigorous lower bound on physical value. So the direction of the inequalities are correct. So if you find any dual feasible point, any point which satisfies these convex constraints, it doesn't need to maximize this, just anything, then that's going to provide lower bound on this guy, and in particular physical value. So now the strategy is to find the finite dimensional ansatz for your Lagrange multiplier and find the optimal feasible point within the finite dimensional ansatz. Okay. And you obtain rigorous lower and upper bounds.
Sorry.
Yes.
So this gives a lower bound. Do you also get?
Yeah. By inserting extra signs, you can also get upper bound. Yeah. So this is resolved for the same one matrix quantum mechanics at infinite n at g equals 1, beta equals 1. This is trace of x tau, x naught as function of Euclidean time tau. And this red region is the bootstrap allowed region. You can also tackle the zero temperature, ground state. Left is the basically same observable as function of Euclidean time tau. This is negative g. As you can see, once you zoom in a lot, you can see this red region, which is coming from basically our tightest bootstrap constraints. And there is a reason why I'm showing you all this precision. Actually, all this extra precision matters. Your Euclidean two-point function contains infinitely many information about your system. If you do the spectral decomposition, then you actually get contributions from all the excited states. So if you get this much of a precision, you can actually extract not just the excited state energy, but also the matrix elements. Okay? So for example, this log plot, if you look at the slope at late time, that's proportional to the gap of the theory. Okay, this is the equilibrium part for the matrix quantum mechanics. And now I'm going to go to the non-equilibrium matrix quantum mechanics side. There are several motivations to consider them. But let me give you one specific motivation coming from quantum optics. Okay, so consider this Hamiltonian. This is single particle. This is not a matrix. Okay, it's a single particle, and this minus sign is correct sign. Naively, you might say it's unbounded. Why do we study it? But if you bring this to your quantum optics friends, they will be very happy. They will tell you to write everything in terms of annihilation creation operator, and then they will tell you that this is Hamiltonian in the rotating frame, where your original Hamiltonian looks like this one. So what is this? So first one describes photons inside cavity with characteristic frequency omega c. You have mirrors, photons trapped in there. Now you shoot a laser into it, so you are pumping the photons into it. And when the frequencies satisfy this relation, this becomes this in some rotating frame. Okay. So there's a physical reason why this is unbounded. It's just that you keep pumping in the photons, so the number operator is going to diverge. That's the unboundedness of this potential. In real life, there's dissipation. So let's model this using Lindblad equation. So again, we are using annihilation operator as a jump operator, meaning that they give rise to the dissipation of the photon quanta. And on physical ground, we expect that if dissipation is low, then your unboundedness wins. Okay? You cannot find normalizable steady state. But if dissipation is strong, maybe it wins over the unboundedness of the potential. And this is the exact answer. So this is number operator at steady state. Below 2 for gamma, there is no steady state, but above it, you find unique steady state. It's normalizable. Okay, so there is this toy example of phase transition in a sense.
Only consider one mode here.
Oh yeah, for here, I just consider this one mode.
This system is you should be able to solve it. No?
Yeah. There's exactly.
Just solve
yeah, exactly. Yeah. You can literally go and solve it. Yeah, and this is the exact answer drawn by my hands. Yeah.
What happens when gamma is exactly 2?
Good question. Basically, the exact answer diverges. It still diverges. For example, your number operator expectation value still diverges. It's given by something like 4 over gamma minus 2 or something like that. I forgot the exact expression. Yeah.
Sorry, question. So you were talked about equilibrium, and now you went to kind of full out of equilibrium, but there's something in between which is also interesting, which is real-time dynamics in equilibrium.
That's right.
Is that something that
For the
is
future.
amenable for the future? Okay.
Yeah, I'm going to mention that.
It sounds easier than easier than this. But
Not quite.
maybe not. Okay.
Yeah, it's more difficult.
Okay.
Yeah. Okay. And then this paper caught my eyes some years ago. So this is called driven dissipative polarized number. Hamiltonian contains similar terms. Now this is one photon laser, and this is self-interaction of the photons inside a cavity. And let's still use the A as the jump operator. Okay. You say this ends here. These guys literally wrote ends here. Okay. And what are these ends? So if you fix all the other parameters to be order 1 and send n to infinity, turns out that your number operator expectation value in steady state scales linearly in n. Okay? And what they found was that there is a sharp first order phase transition when you are at exactly infinite n. Okay? So this is some large n scaling for them, and they find first order phase transition. Surprisingly, this large n scaling is exactly the same as the Hooft limit for the matrix quantum mechanics. So it's simply impossible not to consider such a case. Okay? So that's one motivation. Let me tell you more general motivation. So in the future, hopefully, we can do the quantum simulation of holographic quantum systems, but of course, those are subject to dissipation. So I think it's also timely to consider non-equilibrium effects for such holographic systems. And another thing is that even in quantum gravity theory, if you have access only to a subsystem information, then it's going to obey some non-equilibrium dynamics. So I think these are motivations to consider non-equilibrium holographic systems, in particular non-equilibrium matrix quantum
So
mechanics.
can you go back? Can you just explain that plot? What is the dashed line on the plot?
Dashed line is some semi-classical computation. Yeah. So you can majorly ignore it. These are the numeric, these are the exact results at finite n. And as you can see, as n increases, it becomes sharper and sharper and sharper. And at exact infinite n, there is a sharp first order phase transition. Yeah, this is one of the non-equilibrium phase transitions people studying quantum optics. And has been experimentally verified 2 years ago. So let's consider matrix quantum mechanics at large n with dissipation. So this is annihilation and creation operator for matrix quanta. Okay, so jump operator you choose to be annihilation operator, and this is the Lindblad equation. We can just repeat the bootstrap. We impose positivity and require this to be 0 for this steady state. And for our favorite Hamiltonian, this is a result at positive g. So this number operator, as you can see, decreases as dissipation increases. What's interesting is, again, negative g. So before, for the equilibrium case, there was a critical point. Okay, so you cannot go below this critical point, but in the presence of dissipation, now we know that strong enough dissipation will allow for steady state even below this GC. So using this infeasibility bootstrap, you can rule out this space of gamma comma g, and this red region is basically bootstrap disallowed region. This is the region where you cannot find any normalizable steady state, but outside of it, basically you can find, you are allowed to have normalizable steady state. And I think the holographic interpretation is that you may be able to find stationary quantum gravity background thanks to dissipation. Okay. And this is the quantum optic matrix version of quantum optics problem that I described to you. One matrix quantum pumping, self-interaction. And again, if you consider large n, this is trace x as function of gamma. This is number operator as function of gamma. You see strong signature of non-equilibrium phase transition. Okay. So, in recent years, people have found non-equilibrium phase transitions in various fields of physics. And I think what this is suggesting is that probably quantum gravity is not an exception. Okay.
So what is non-equilibrium about it?
Sorry?
In the gravitational context, what do you have in mind producing the non-equilibrium?
Great question. So I do not have good picture about the holographic dual of these specific models. But one thing that you could imagine is that you can, for example, subject your system to some heat bath, which is basically absorbing some quanta at some rate. Actually, kind of similar to, say, island story, where people actually subjected boundary condition, which is kind of, extracting. And that's how they model the black hole evaporation. I mean, similar, but not exactly the
So
same.
you have in mind just coupling some holographic system to a heat bath?
That's right. That's right. Yeah, that's the simplest that I can think of. But I think black hole evaporation setup is kind of similar in that sense, because it's some subsystem and it's kind of evaporating quanta to the environment. Yeah. One thing that I'm still yet to understand is to, for example, if you take C equals 1 matrix quantum mechanics where you have explicitly holographic dual C equals 1 theory, I'm yet to be able to figure out how to work this non-equilibrium physics to the string theory side. That one I don't know. But it's going to be interesting. Yeah. Okay, I have 10 or so minutes to tell you about quantum spin change. So far it was about matrix quantum mechanics, string theory, quantum gravity. And now let's move on to more like qubits. These are just another quantum system, so you can run basically the similar argument, except that there are some conceptually different things at the practical level. So consider your favorite transverse field Ising model on a chain. This is just 1D Ising model, okay? It's exactly solvable. And Bootstrap, of course, applies. But number of variables and constraints grow exponentially as you try to include more side operators. So it becomes pretty tough very quickly. So that leads to the idea of coarse-grained Bootstrap. So Bootstrap gives you infinitely many constraints. Maybe you don't need to consider all of them. You can select only some relevant subsets. Okay, and this is tied to the idea of using tensor networks to describe the low energy physics efficiently. In this paper, these authors found matrix product state based Bootstrap, which gave very precise lower bounds on the ground state energy.
Why is it tied to a tensor network?
Yeah. So basically, in tensor network, the reason why it's good at describing low energy physics is because in this exponentially huge Hilbert space, there are only very tiny subset of the states which are relevant at low energies, and tensor network is kind of directly parameterizing that most relevant states. So similarly, you might ask, in the Bootstrap constraints, are there most relevant Bootstrap constraints? That's basically the question. And what this guy did was the following. It's called reduced density matrix Bootstrap. So here's the full Bootstrap problem. So here, rho of n is a reduced density matrix where you trace over all the infinitely many qubits except for m consecutive sides. Okay, so it's literally the reduced density matrix. And you want to minimize the energy subject to normalization, positivity of all these reduced density matrices together with their compatibility condition. If you have qubit here, if you trace it out, you should get lower reduced density matrix. That's what this is saying. Okay. So of course, this is a huge problem. And what these guys did was to introduce MPS. So this is matrix product state. So if you're not familiar with it, just think of this as some tensor with 3 indices. One index is qubit index. The other 2 are auxiliary indices ranging over something called bond dimension. What they did was to, contract all the internal indices of reduced density matrices using this B tensor. And then they landed this omega tensor, okay? And this omega tensor must be positive because you simply just took the edge action. And also they obey their compatibility condition, which follows from this guy, okay? But the good thing is that the number of variables in this omega does not grow with n, okay? And the constraints also does not grow with n. So it's only linearly growing number of constraints, and that's how they were able to get very precise bounds.
Sorry, what is this W? WM? What's the difference in W?
Yeah, so it's basically some conjugation of your density matrix rho in a manner that you contract all the internal qubit indices using this tensor net, MPS. And you just define this W to be this one. So it's kind of a coarse-grained reduced density matrix.
But it still has some D, it still has some auxiliary indices, right?
That's right.
So it's not
D,
quite.
D. Right. Yeah. But the thing is that that's something that stays constant. Yeah. And our contribution was to basically extend all of these things to the equilibrium constraints that I described to you before. And the end result is something like this. So this is transverse field Ising model. This is Z0, Z1. And this black curve is the exact answer. This green dotted line is basically without any coarse graining. It's pretty loose, but as soon as you introduce coarse graining in the symmetry unbroken phase, it nails down the answer. Some of these precisions are actually beyond what DMRG can give you. This is a region where long range order enters. That's the reason why bounds are not that good. But actually, very recently, Eslam Khalaf, Michael Scheer, and collaborators found a way to deal with this long range order, and this bound is also now very tight in their paper. And this is for the, this was for the ground state. This is for the non-zero temperature, and you again get meaningful improvement using the coarse grain. Now let me move on to the spin chain, which is non-equilibrium dynamics, okay? I'm going to tell you about one specific example called quantum contact process, okay? This one, we are still working it out. We started to get the results just yesterday, okay? So the results that I'm going to going to present to you are very preliminary. So it was devised by these people. If you are familiar with the directed percolation universality class in STEMMAC, this is basically a quantum version of it. So this is Hamiltonian, usual Pauli matrix X, Y, Z. And this N is roughly speaking the number operator. It's kind of, counting the upspin in a sense, upspin component. And this dissipation term, jump operator, we are going to take this combination. Sometimes this is also written as sigma minus. It's basically the operator which kills the up qubit, okay? So what's happening is that if you have up qubit here, that's going to require your neighbor qubits to, switch with each other, down and up spin. That's what X operator does. This LK is, spontaneously from time to time, just going to kill the components along the up spin, okay? What that means is that regardless of the value of gamma and omega, actually we are going to set gamma to 1 because we only consider the ratio. There is always a steady state called absorbing state. If all the qubits are to begin with down, it's going to stay invariant forever because this is kind of killing the up component, and this is activated only when you have non-zero up component. So this absorbing state is always a steady state. Now the question is, are there any other steady states? That's the question. And the expectation is like the following. So if your omega is small, then basically you have no chance of maintaining quantum coherence. So this absorbing state is going to be the unique steady state. However, when your omega is large enough, then you may be able to maintain some quantum coherence, and you may be able to find non-trivial steady state. And this is, roughly speaking, the answer. So you consider Z expectation value. Below some critical value of omega C, which is roughly 6, you actually see that it's just -1, meaning that this is region where absorbing state is the only steady state. However, beyond that, you are allowed to have non-trivial steady state. Okay, so this is non-equivalent phase transition, and this transition point belongs to the has relation to the directed percolation universality class. So it seems nice, and we were wondering if we can actually get any bounds on this omega C, just along the line of bounding critical temperature and so on. And turns out that the answer is yes. Okay, you just plug in all of these things into Bootstrap. This is very preliminary result, and you get this upper bound on this Z. Okay, and very nicely, say you consider only up to 4 side operators, you see that this must be just identically -1 up to some point. Okay, so Bootstrap tells you that below this point, absorbing state is the only steady state. And likewise, if you increase it, it rapidly increases. Okay. So in the end, we want to get somewhere near 6. We are far from it, but the behavior seems pretty quick. Another thing you can do is to study something called Liouvillian gap. Okay. Consider the subcritical phase. So this is where absorbing state is the only steady state, meaning that if you time evolve enough, any initial condition is going to approach absorbing state. Okay. But there's exponential tail, and the leading exponential tail is related to this number, this exponent delta. And this delta is basically the Liouvillian gap. It's roughly speaking gap in the spectrum of your time evolution operator. It's the real part. The thing is that positivity of density matrix and Lindblad master equation, Lindblad equation, they must be true at any t, in particular at late t. What that means is that you can literally plug this into these constraints. And then if you look at this ddt term, it's gonna bring down factor of gap, okay, this delta. So now you have constraints which are sensitive to your value of the gap. And you can play this infeasibility game again. You try a trial value of delta. And if you find it infeasible, you know that trial value is ruled out as the value of the spectral gap. And here's the preliminary result that omega equals 0.3. So this is a bootstrap cutoff. You can see that, so these are upper and lower bounds, and you can see that it quickly approaches each other. So this is how you can get lower and upper bounds on the Liouvillian spectral gap. Okay, this is what Luca already alluded to. So this is future directions. Lorentzian two-point function is another interesting thing. So today we discussed Euclidean two-point function. You can also consider Lorentzian two-point function. In chaotic case, you expect in the holographic case, you expect to see black hole quasi-enormous, which has attracted lots of attention in recent years. And this is another thing which I already alluded to. It would be very nice if one can work out holographic dual of all these non-equilibrium matrix quantum mechanics. And I have to tell you, similar bootstrap approach applies to other type of setups: classical step max, stochastic processes, dynamical systems, even disordered average, quantum circuits, and so on. And for these highlighted ones, I plan to give a talk covering these guys at the UIUC and UChicago joint workshop that Luca announced this lunch. Yeah. And this is my last slide. So a few years ago, I organized a workshop named Positivity at Princeton, and Igor Klebanov recommended this song to us. Name is Essential to Positive. It's a song written in 1944. Okay? It's a nice song with beautiful lyrics. So let me share with you. You got to accentuate the positive. So they know that density matrices must be positive. Eliminate the negative. So they know that when positivity is violated, you should rule that out as a valid physics. They further talk about maximizing joy, minimizing bloom. Okay? So I take this as evidence that they already knew about bootstrapping in 1944, and hopefully we can make up to their expectation. That's all I have for today.
Yeah, maybe a general question. So the results and plots you get are kind of very model dependent, right? You just change the coupling, you have a new plot.
That's right.
Do you think there's some kind of general, maybe weaker bounds one can get on a class of Hamiltonians? You see what I'm saying? Maybe you say what you postulate what the degrees of freedom are, and
yeah,
is that something that's possible?
In principle, yes, because all the say. So here, basically, say you just provide Hamiltonian, parameterize your Hamiltonian with some generic class of couplings. Then APRA, all these constraints know about basically generic G. But in order to make some strong statements about, okay, for all G values within, some valid region, you are expecting this and blah, 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 that typically requires more care. And one of such examples are, one cases where such statements can be made are things like ferromagnets. There, we know some strong type of monotonicity properties, where, depending on the parameter, your expectation values are always monotonic in some fashion. So in such cases, you can make such an argument pretty easily. For general cases, I'm not sure. I think it's very case dependent. Yeah. Yes.
So a lot of this is dependent on all these constraints are coming from thermal equilibrium, chaos conditions. So is there something you can do when the canonical ensemble doesn't exist, like Hagedorn thermodynamics?
Hagedorn, good question. So, right. Right, you're having in mind where your energy is of order n to the 0 in low temperature, but then after Hagedorn phase transition, it develops n squared. That's when you have in mind.
Right, but you can't. Well, I guess you would be pinned to, I guess, a fixed temperature, which is the Hagedorn temperature. But
so this large matrix quantum mechanics bootstrap, I can imagine that it's going to tackle the deconfined phase, because that's exactly the same scaling of large n that we discussed here. Below the Hagedorn temperature, I'm actually uncertain what one is going to find. Maybe one is going to find that, just like the case that we studied today, there is simply no thermal equilibrium. Maybe that's going to come out as a result, just like this plot. So this plot is kind of a reverse of Hagedorn in the sense that below this temperature, you can find thermal equilibrium. Above this temperature, you cannot. Yeah. So it's kind of opposite.
But there is some interesting statistical physics you can do when you're in the Hagedorn phase, where the temperature is fixed, and you work in the microcanonical ensemble.
Oh, sorry. Are you fixing the temperature to be the Hagedorn temperature?
Yes.
And I see.
And I look in some energy window and ask about observables.
Oh, I see.
Is there anything you can bootstrap in such a situation?
Good question. I haven't thought about it, but let's see. So fixed temperature, of course you can get all these expectation values, but now the question is, can you get microcanonical ensemble information out of it? If you have good enough resolution for the all the operator expectation values, then in principle, the answer should be yes. You should get some information. But whether that's going to be practically doable or not, I don't know. Yeah. especially because it's exactly at the Hagedorn phase transition. So at the criticality, typically bootstrap is quite funny. So here you can see this nearly incompatible bootstrap bounds, and that's presumably what's gonna happen.
Well, the system wants to run away, right? It wants to run away by just extracting an infinite amount of energy from the heat bath.
That's right. That's right. Yeah. So I don't know. I think it's an interesting thing to try, but at this point, I cannot make any prediction. Yeah. Yes.
Do you have intuition on when bootstrap is useful for, or for which problems? So far, it's every problem you think, or
No, I try to constrain myself from committing too much about the power of bootstrap in some specific problems. Yeah, I mean, just because you can bootstrap it does not mean that it's the most powerful tool. So yeah, it's really case dependent, I would say. Yeah, for the, say, matrix quantum mechanics, it was a very powerful tool because it can directly tackle infinite n. Right? So it's, I guess, like, this is so far the only way to tackle some of the interesting problems in large n matrix theories. Yeah. But for the spin chain case that I described, it's not the only way, in a sense. Like, we already have tensor networks working very well and so on. But you might be able to come up with some problem of, you are given some specific problem in condensed matter where you want to show that there is some non-zero gap in the theory, and that's actually important. Then those type of problems are something that bootstrap may be able to tackle. Any non-zero lower bound on the gap would suffice. So if those are the types of the question that you are interested in, maybe you can just forget about the power of bootstrap, but just use it as a technique to prove something. So I think it's really case dependent. Yeah. I mean, I initially got interested in bootstrap via conformal bootstrap, where it was very powerful tool. I mean, by now conformal bootstrap is a very powerful tool in studying CFTs. And there are this type of examples where it works really well, but I don't know, I don't know general criteria when it's guaranteed to work well.
so. I mean, you mentioned that it's better when you have a gap for like spin chains, for example.
Okay,
And
so
when you don't have a gap, then maybe maybe that could just a formal bootstrap or something like.
yeah, good point. Indeed, like one thing you might say as a bootstrapper is that this bootstrap is bad around criticality, but at criticality you can just use conformal bootstrap.
Yeah.
That's one thing you can say, of course. Yeah, yeah, of course.
There are no more questions. Let's thank Minjae again.